Hello everyone. In this video, I'm going to explain a single slit diffraction. In particular, I'm going to focus on the nature of single slit diffraction, describing the effect of slit width on the diffraction pattern, and determining the position of the first interference minimum. This is HL material topic 9.2, although important for SL to understand qualitatively, so without the formulas. The phenomenon I'm going to explain is single slit diffraction. This happens when you shine laser light, for example, on a very small slit. Okay, and we've seen the double slit interference pattern. When light is shown on a double slit, you get an interference on the back wall. As it turns out, when you shine the same kind of laser light on a single slit, you get an interference pattern on the back wall as well. This is quite remarkable for reasons we'll discuss in a moment. So what you actually see on the back wall looks like this. You shine that laser light, in this case red laser, and you see that there is a central maximum surrounded by two primary minima, and then two secondary maxima. And that pattern repeats, although it gets dimmer. If you were to graph that, you would see a central maximum right in the middle of the intensity curve, and then a primary minimum right next to it, and another maximum, so on and so forth. And those secondary maxima are at most 5% of the intensity of the central maximum. Unfortunately, that is something you need to know. So, why does this happen? This is a fairly surprising phenomenon. It's as if you took a light and you shone it through a window or some kind of crack. On the back, behind the crack, you would expect to see sort of an outline of that opening, but you don't see that. You see something else. You see an interference pattern. And this is particularly unusual because we explained the double slit pattern. We explained the interference pattern for a double slit, but it depended on there being sort of two sources. You got interference between two sources. The fact that you see an interference pattern for a single slit raises the question, what exactly is interfering if there is only one source of light? To explain that, we need to back up just a little bit and remind ourselves of Huygens' principle. Huygens' principle stated that every point on a wavefront acted as a point source of outgoing circular waves, which interfere to produce the next wavefront. The idea was that each point along this wavefront produced circular waves, and where those waves overlap, you get destructive interference, but they all align at exactly one point, which is right along the next wavefront. And so the result is that we have taken what seemed to be a pretty straightforward phenomenon, which were these plane waves, these planar waves traveling forwards, and we made it more complicated. But that allowed us to explain diffraction, because when that wavefront gets to the aperture, the points that would have been here are not. And as a result, there's no destructive interference. And these points right here produce circular wavefronts that bend, okay? And so the whole wave sort of bends around that aperture. Okay? But the key idea is that what is underlying this explanation is that every point in the wavefront acts as a point source of its own outgoing circular waves. This will allow us to explain the single slit diffraction pattern. To do that, we're going to zoom in on this diagram right here. Okay, and what we're going to focus on is the point where you get that primary minimum. Okay, so the first point over here on this graph where that intensity is 0. Okay, that happens due to destructive interference rather than constructive interference. So that raises the question, what exactly is destructively interfering? And the thought experiment is simple. If you take your slit of width B, notice this is a slit of width B, then you will see that each point in the top half of the slit is producing circular waves, and each point in the bottom half of the slit is also producing circular waves. And so the answer to the question, what exactly is interfering, is that every point on the top half is interfering with its counterpart on the bottom half of the slit. So A1 is interfering with B1, A2 is interfering with B2, and so on and so forth down the line. Okay, and if we're talking about destructive interference at that primary minimum, then what we're talking about is A1 interfering with B1 destructively. And the argument about how they interfere is exactly like the double slit argument. And so you can see that even though the single slit phenomenon is more simple than the double slit phenomenon, right? There's only one slit. The explanation of single slit diffraction depends on the explanation of double slit diffraction. So like on the double slit, in the double slit case, we say that light is coming from A1. It is a point source according to Huygens principle, and light is also coming from B1. And they are interfering destructively exactly when the extra distance that B1 has to travel is equal to lambda over 2. So the primary minimum occurs when you get destructive interference, and you get destructive interference first when the path difference here, the difference between A1 and B1 to the wall, is exactly one wavelength divided by 2. Things are exactly offset, and you get destructive interference. So we say the path difference then is equal to this side of the triangle. And we can use that fact to derive the formula or the relationship between the angle of that primary minimum and the wavelength. So we say that the path difference here is lambda over 2, and it is equal to this side of this triangle. But the side of that triangle, this side of that triangle, is equal to b over 2, the hypotenuse, times sine theta. Okay, so the hypotenuse of this right triangle is b over 2. So you multiply by sine theta, that gives you this distance right here. And just like in the double slit case, we're relying on the fact that theta, the angle to the screen, is the same as this theta right here. So that means lambda over 2 is equal to b over 2 sine theta, and our 2's cancel, leaving us with lambda over b equals sine theta. But we also make use of the fact that sine theta is about theta for small angles. This is the small angle approximation. It also means that theta is now in radians, has to be in radians. And that gives us our fundamental relationship between the angle between the central maximum and the primary minimum, and the wavelength and the slit width. Notice that although the argument, the qualitative argument, depended on dividing that slit width in half, the final equation does not. So the angle between the central maximum and the primary minimum, this angle right here, is equal to lambda over b, the wavelength divided by the slit width. We can compare this directly to the double slit phenomenon, and it's important to keep them straight. So that angle, theta, equal to lambda over b, is the angle between the center of that central maximum and that primary minimum in the single slit case. That is different from the equation in the double slit pattern. For the double slit pattern, that is S equals lambda d over d, which is an equation governing the fringe spacing. So the distance between all of these dots right here. Notice that the double slit pattern is finding the distance between the bright spots. The single slit pattern equation is finding the distance between the center of the middle bright spot and that first dark spot. Okay, so that's important to keep track of. The final thing we're going to explain is the effect of slit width on the angle between the central maximum and the primary minimum. Okay, so how does B right here affect theta? And that is straightforward to explain. We can see that theta is inversely proportional to B, and as a result, when B increases, when the slit width increases, you would expect an increased angle, angle between the central maximum and primary minimum. In particular, if you double the slit width, as you can see in these two graphs, in graph B has double the slit width of graph A, and therefore you get a narrower peak. Okay, so theta right here is half the size of theta on this graph. Notice that in this graph, the axis of part A is mislabeled. Okay, so this is mislabeled. They should be the same powers of 10 on each of these axes. But that is the relationship between the slit width and the angle between the central maximum and primary minimum. One more thing to note, okay, one final note, which is that this derivation allows us to explain something that you have memorized and stated, but we have not explained, which is that in order to see diffraction effects, diffractive effects, you need to have a wavelength roughly the size of the slit width. In this particular equation, you can see that if lambda is bigger than b, because sine theta equals lambda over b, notice we're using sine theta because it is more correct, and we're going to consider large thetas here. Then if lambda is bigger than b, that means sine theta would be bigger than 1. That's impossible, and so you can only see the central maximum if the wavelength is bigger than the slit width. If the wavelength is much, much smaller than the slit width, though, so if lambda here is much, much smaller than b, then theta is about equal to 0. And so you can't see any diffraction effect at all. So in order to get a single slit diffraction pattern that's clear, you need lambda less than b, and you need it to be around the same size, okay? And this is a quantitative explanation of something we have said qualitatively, which is that diffraction in general depends on the wavelength being at least approximately the same size as the slit width.